So just a couple misconceptions, mistakes, or just things that I felt like was important to mention. Make sure that I talked about them specifically so that you knew that they were there relating to rotational motion. The first one is that I have shared with you guys an equation that says that the, um, the linear velocity is equal to r omega. But that's not actually always true. So for example, if I was talking about just a wheel spinning and I wanted to know what the linear velocity of a single point was, we can use it there. But where it becomes an issue is if we dropped like a spinning wheel onto the ground and we were looking at the linear speed of the wheel versus the angular speed of the rotation of the wheel. If it doesn't slip, then the velocity here would be exactly the same as r times the angular velocity. Because every time that it makes a full rotation, it's going to have to move forward that full circumference of 2 pi r. But if it's slipping, if friction's not good enough to keep it from moving, then potentially that wheel could be spinning much faster than you're actually moving forward, which would be a lot more helpful if we ever got snow in Southern California. But you guys would be like, oh yeah, we can totally have a huge angular velocity without having any linear speed. So just be aware, for the most part, you can use this equation as long as we're looking at a situation where there could be a direct relationship between linear velocity and angular velocity. So just be watching for that if that comes up in a question. If it talks about it slipping and stuff, that's a hint that they're checking to make sure you understand when you can use this relationship and when you cannot. All right, the next one that's pretty important is to realize that objects that move in straight lines can be described in angular terms. So the misconception is that it can't be. And I've got like a ball traveling in a straight line. And so if I asked you, what's the angular speed of this object? Most students would say, well, it has no angular speed. There's nothing happening angularly? Sure, rotationally, that's probably a better word. There's nothing happening rotationally here at all because it's going in a straight line. But where that's a mistake is because we're not looking at the fact that we could be talking about a different point for our rotational or angular coordinate system. And if we did use some different points, we could see that there is an angular motion here. So an example of that is, let's imagine that I'm talking about relative to this point right here. Relative to that point, it is starting here and it's moving there. You can imagine that that is part of a circle and we have an angular rotation I'm still on calculus mode because of the last video I did. We have a change in angle that occurred right there. Now, it didn't actually move along this line, but if we were talking about a rotational or an angular velocity there, we could say its angular velocity would be equal to that change in theta over time. And a lot of you guys are like, okay, well, is that actually useful? Where would you ever use something like that? And it does come up. In fact, in the chemistry class that I was teaching last year, I couldn't really get into this because the chemistry students didn't have the physics background to think about it. But we talked about fire tornadoes. And one thing to think about with fire tornadoes is that we have this spinning vortex right here, and we have wind that travels in what seems to be straight lines. But relative to that vortex, it actually is changing an angular velocity. It does have an angular velocity relative to that vortex. And so when it starts spinning around, it's not that it just started spinning out of nowhere. It's actually been relative to that center of rotation, spinning the entire time. It just hasn't been changing its linear direction until it gets closer to the vortex. So just be aware that for any linear problem, you could rewrite it as a rotational motion problem. Often there's no point to doing that, but that kind of leads into our next big misconception. And I'm going to be honest right here, this misconception isn't going to be coming up for another few days because we haven't talked about angular momentum. But I want to bring it up now because the more times I mention it, the better chance we'll have of having it stick in our brains. So for this one, in the bottom left corner, let's imagine that we have a ball or like a hockey puck or something like that that's going towards a rod that's sitting on the ice. And the reason why I'm putting it on ice is I just want us to ignore any outside forces. Let's just say that both of these things, other than their interactions with each other, aren't being acted on by anything else. So when this object, it's moving, hits the board, the board is going to start sliding this way because it got hit and it's going to start moving horizontally. And that's going to conserve the linear momentum. No matter what happens with the other piece, the linear momentum would be conserved. If it sticks to it, they would both have a linear momentum continuing just to the right. Or if it bounced off, maybe the ball would go off in this direction and the whole board system or the board would start moving slightly up to conserve angular or linear momentum. But angular momentum is also conserved, and it's conserved separately. And this is where students have a hard time because they're looking at this and they're saying, well, there's only linear stuff happening before. But if we talk about the center of mass of our system, which is probably about here, then as that ball is coming closer in, it does have a rotational or an angular velocity relative to that center point. So that when later that ball moves off this way and the board itself starts rotating as it moves upwards, or however it happens, we didn't just create angular momentum. Relative to our center of rotation, we had angular momentum the entire time. So they're not interchangeable. Linear and rotational motion are two totally separate coordinate systems. So we can talk about them separately, but you can't linear doesn't turn into angular. They're just two ways of looking at the same scenarios. So both momentums are conserved because they're both different ways to look at it. And if one of them's not conserved because there's an outside force, it's not that it turned into something else or the linear turned into angular. It's just maybe linear wasn't conserved and angular was. I feel like I have to explain what I mean by that. If this rod was stuck in place when that ball came in, then it would start spinning, but it wouldn't have linear momentum conserved because the outside force of that, whatever normal force that nail that holds it in place has, would keep linear momentum from seeming to be conserved with the system that we've described. We can also have something where angular momentum is not conserved, but linear is. But that doesn't come up that often, and it's like a really convoluted scenario. So I'm just going to not talk about it. Last thing, the last big misconception is that students talk about centripetal and angular momentum, or centripetal and angular acceleration, and think of them as being the same thing. Like they both sound like circle stuff. They both have the word acceleration, and so students try to use them interchangeably, but they're not interchangeable. If I'm talking about angular acceleration, I'm talking about the change in velocity. I keep using calculus notation. The change in angular velocity over time. So that's angular acceleration, and it has to do with how fast it's spinning. Centripetal acceleration has to do with the acceleration of a specific point as it's changing direction. Centripetal is really a linear motion term that describes something that's moving in a circle. Angular momentum or angular acceleration, man, I keep saying momentum. Angular acceleration is talking about the rotational reference frame. And so if we're talking about rotation, it's angular acceleration. And if we're trying to describe an object that's turning, but otherwise doing linear motion, we would use centripetal acceleration. So make sure that you separate those two quantities in your mind and you don't make kind of a classic mistake of on an FRQ talking about one when you really should be talking about the other, or you don't fall into just what is a pretty obvious trap if you're watching for it, but a trap on multiple choice questions where they throw something in there about centripetal acceleration, even though it's a rotational motion problem, knowing that students have probably struggled with and talked about centripetal more. They know that students will sometimes pick that without really thinking about it. So one more time, centripetal describes a turning object that's otherwise undergoing linear motion. Angular motion describes the change in angular velocity within a rotational motion reference frame. All right, so those are some of the bigger misconceptions, mistakes, and warnings that I can give you guys for this unit. Thank you so much for watching. Have a great night.